So this is the last video on this series, and it is about evaluating the integral algebraically. So far, just recap, we've been doing it through Riemann sums, and that was just an approximation, whether it was right, left, midpoint, trapezoid. Those were all approximations. We can also use Math 9. We can use geometric formulas to try to come up with that net area if the graph happens to lend itself. But we really don't have a way of doing it algebraically. Well, the fundamental theorem of calculus, part 2, is really, that's what it does. It tells you how to take the integral. Hopefully we already have established the meaning of it, meaning the net area under the curve f of x from a to b. And now you're ready to compute it algebraically. And I always like to start with a little, the way I think about it. And I like to use velocity, position, displacement to explain it. And then we'll go over the formal theorem. I'm not going to prove it, but the proof is not that complicated. If you're interested, we can talk about it at a later time. So one of the things that I like to do is I let velocity equal f of t. So I will let velocity equal f of t, or in this case, I'll just call it f of x. So let's just, instead of calling it v of t, let's call it f of x. So and you remember the relationship is that given position, the derivative of position is velocity. So backwards, the antiderivative of velocity would be position. And our notation for antiderivative is capital F of x. So instead of using s of t or v of t like we used to before, let's just use f of x for now. So again, the velocity is the derivative of position, or the reverse way would be to say that position is the antiderivative of velocity. So we'll let velocity be little f of x, and we'll make position capital F of x. So a question is, well, what would be the change in position? How would we denote that? Well, if we're looking at an interval from a to b, our change in position would be, of course, the position at time at b minus the position at a. And if you remember, the change in position, the final position minus initial position, we called that displacement. And I've been saying this already in class, and I keep telling you that the integral of a function is not its distance, it's its displacement. And so here, this is a huge idea. What we're really saying is that our change in position is given by capital F of b, meaning the antiderivative of the little function at b minus the antiderivative of the little function at a, and that really that is equal to the integral from a to b of f of x dx. The actual theorem states, this is fundamental theorem of calculus part 2. The actual theorem states if f is continuous at every point in the interval a to b, and if the antiderivative f of the function, and if capital F is the antiderivative of f on a to b, then the integral from a to b of f of x dx is simply, and I know you're going to think this is too easy to be true, but it is. It's the antiderivative of b, the top boundary, minus the antiderivative of a. And if you haven't written this down, you might want to press pause and write it down, because this is very, very important. So this is how we're going to use that theorem that we just wrote down. We have the integral from a to b of f of x dx equals f of b minus f of a, where f is capital F, represents the integral. So the way we're going to set this up, take the integral from 0 to 4, we're going to first find the antiderivative of x squared. So we're going to go ahead and take the squared, we're going to add 1, and then that's 3. We'll multiply by the reciprocal. So the antiderivative will be x cubed times 1/3. and that's just the antiderivative of x squared. I always start with what I do instead of this, because we're about to take the integral, so what I do is I put a little here, it's supposed to be just like a long line, if you will. It's really just a placeholder to remind me that my boundaries are 0 to 4. So I took my antiderivative and I'm going to be using 0 to 4. Okay, so what happens next is I go ahead and plug in the 4 into the x. So I have 1/3 times 4 cubed. And that is this part right here, the f of b, the antiderivative of b. This is b, this is a. Then we do minus 1/3, and then it should be 0 cubed. So all I did was plug my boundaries in the order of b and a into the antiderivative. This whole thing is easy. It's just going to go to 0 because 0 cubed is 0 times 1/3 is 0. And then we're just going to have to do 4 cubed, which is 64. So we end up with 64 divided by 3. And I know that that's not divisible by 3, so I can just leave it as a fraction. And that's the answer. This represents the net area under the curve from 0 to 4 if the curve is x squared. Excuse me, x squared. So let's try a different one. Just going to go ahead and erase this. And I'm going to switch over to a different one. Okay, so now I'm taking the integral from -1 to 2 of 4x minus 2. I'm going to go ahead and take the antiderivative of 4x minus 2, this quantity here, and I'm going from -1 to 2, so that's my placeholder. So the antiderivative of 4x squared, 4x, excuse me, is going to be 2x squared. Again, we add 1 to the power and multiply by the reciprocal, so 2x squared, minus the antiderivative of 2 is going to be 2x. And I like this problem because it has two terms with x's in them, and you're going to see how to deal with that in just a second. So I'm going to take my 2, plug it into every term that has an x. So both the first term and the second term, they both have x's. So I need to make sure I do the 2 goes into both of them. Oftentimes, students will forget to plug it into the second one. So what they'll do is they'll plug in the 2 into the first term and the -1 into the second term, but that is incorrect. You need to plug the 2 into all of that antiderivative, both terms. Okay, so this is the f of b part. And now you need to plug in a -1. So it's going to be -2 times -1 squared minus 2 times -1. Now, something that's really important here is that you subtract the entire f of a. So here's where my f of a starts. So it's very important that I put parentheses around the entire thing, because there's two terms and that negative needs to apply to everything, not just the first term. So of course this becomes 4 times 2, which is 8, minus 4, so this becomes 4. That's the f of b. This becomes 2 plus 2, which also becomes 4. So I end up with 4 minus 4, and the result is 0, which is totally okay. Just means our displacement was 0, our net area canceled out, and we ended up with 0. Okay, let's erase this one. We have a couple more to show. Switch it off. Okay, let's do one with sine. Okay, let's take the antiderivative of sine. Now, the antiderivative of sine from 0 to pi, it's not really cosine, because if you think about it, the derivative of cosine is negative sine. So if we want to get a positive sign, this actually has to be negative cosine, okay? So here we go. We have negative cosine of pi minus negative cosine of 0. So cosine of pi we know is going to be 1. So, excuse me, negative 1. So we have negative times a negative 1 minus minus gives you a plus, and cosine of 0 is 1. So two negatives become a positive 1 plus 1, and the result is 2. And there it is. I believe we did this problem in your notes using Math 9, and we got 2. So now you have an algebraic way of doing that. All right, last one. Antiderivative. Ooh, that's interesting function. It's got a square root. That's not a problem. We're just going to think of this as x plus 2 to the 1/2. Okay, let's see. We're going to take this and we're going to add 1, which is the same as 2 over 2. So that's going to become 3/2. So x plus 2 to the 3/2. And I'm going to multiply by the reciprocal of 3/2, which is 2/3. Now I'm just going to check, because I'm a little nervous about this x plus 2. I'm going to go ahead and check that, in fact, that derivative of this is square root of x plus 2, or x plus 2 to the 1/2. When I bring my 3/2 forward, 3/2 and 2/3, that becomes 1. So that's perfect. And then when I subtract 2 over 2, that becomes 1/2. And using chain rule, the derivative of the inside would have been 1, so times 1. And if I simplify that, I get 1 times x plus 2 to the 1/2 times 1, which is exactly what we started with. So good, I got the antiderivative. Go ahead and take away the red stuff. Okay, so this is my my antiderivative. Again, I'm going from 0 to 1. Okay, so what I'll do is I'll go ahead and, plug in my 1. So I get 2/3 times 1 plus 2 is 3 to the 3/2. And then minus 2/3 times 2 to the 2/3, 3/2. Okay, and that's it. Now I just have to simplify. This is going to be a little bit harder than I thought. So I'm going to press pause and have my calculator help me out here. Okay, I didn't really want to use a calculator, so I just kind of changed this into that's not correct. Neither is that. I'm going to change it into, it's going to be the square root. This is your index, this is your exponent. So it should be the square root of 27 and the square root of 8. So these probably can be simplified even further, but in the end I'm going to get something with the radical. It's not going to be exact, so unless I use a calculator, it's not going to be, an exact number. It's going to be some sort of decimal. So I'll go ahead and leave it there, but most important thing, you want to take the antiderivative, use your line as your placeholder, so it reminds you what boundaries you're using. Plug in your b, make sure if there's more than one term, you plug it into both or all of the terms, and then plug in your a and make sure you subtract. And that's it. This is how you evaluate an integral, so you can now try the third section of the worksheet and see how you do. Let me know if you have questions.